Now at the top of the page is information you provided on the lab sheet with your sample. It is important to use the same equipment reference ID and/or the component reference ID so you can see data on the same component over time and look for trends. Another option is to use the lube analysis number. This unique number will be given to each unique equipment component after the initial sample is processed. The comments section includes lab-provided information helping diagnose any abnormal results. Here you can see an extreme example where several items were flagged and a possible cause for each is provided. We seldom see all of these in one report. However, low viscosity due to fuel dilution and contaminants from the coolant system are common findings. If you have provided a sufficient equipment description, such as describing the make and model of the engine, the lab can indicate what internal components could have caused the appearance of any wear metals. This area is again information from your lab sheet. It is important to include items such as lubricant life so you can see how a lubricant holds up during different oil drain intervals. The first component we will look at in the actual raw data is viscosity. We want to ensure that the lubricant is staying within the tolerances for a given viscosity grade. If the lubricant has fallen below grade, we will then look at fuel dilution, as that can cause a drop in viscosity. You can see here that the fuel dilution has caused the oil to drop viscosity, but it is still within grade. If viscosity is above grade, we may look at TBN, as a low TBN may be a sign of oxidation, which increases the viscosity. So what is TBN? Well, if you have a chemistry degree, total base number measures a lubricant's alkaline reserve, or its ability to neutralize degradation acids and counter oxidation. Here is an explanation for the rest of us. Engine oil will become acidic as it is used. Sulfur contaminants from exhaust, used elements in the additive package, and oxidation all increase the acidity of your oil. The total base number indicates the oil's ability to deal with this increasing and harmful acidity. But simply, TBN is a good indicator of the life expectancy of a lubricant. TBN usually starts about 9 and will decrease as the lubricant is used. As you can see, TBN depletion after 9 looks like an upside down hockey stick. It is a fairly steady depletion until the acid reaches a point that the base additives can no longer neutralize the oil. Around 4, the TBN begins decreasing exponentially and you are nearing the life expectancy of the oil. How far below 4 you can go requires more information on your equipment and lubricant than I want to cover in this general tutorial. So analyzing TBN over time is a good indicator of the quality of oil. Higher quality oils will have a TBN that decreases slower. But don't be fooled by a lubricant's starting TBN, as some lower quality oils may actually start with a higher TBN only to mask its inability to retain TBN over time. Viscosity and TBN are the key components we look at when considering extended drain intervals. Assuming that wear metals, fuel dilution, and contaminants are all within norms, oil drain intervals can be increased as long as the viscosity stays within grade and the TBN does not fall below minimum levels. Water and soot are both considered contaminants and should be at minimum levels. Now we want to look at the parts per million of elements found in the oil. This portion is broken into 3 sections. From iron to vanadium are your wear metals. These elements make up different components inside your engine or equipment. Click here for the chart explaining what elements are found in different components of your engine. Silicon, sodium, and potassium are contaminants, and they are often signs of a coolant system leak. Molybdenum to zinc are elements found in different additive packages. I will often look at the additive package when a lubricant's viscosity is out of grade, because this may indicate additives that are not found in the reported lubricant, and is evidence that another lubricant is present. You can see here on this gear oil that viscosity was flagged, but based on the high amount of boron, we can assume that a different lubricant was added, and it was likely a different viscosity. Thus, the viscosity is now out of grade. Last is fuel dilution. I have mentioned that fuel dilution can cause a drop in viscosity. but it should also be viewed as a contaminant as it is a poor lubricant. Dilution will typically be flagged around 2%, and anything over 5% is a major concern. Causes can include leaking fuel injectors, piston ring blow-by, or excessive idle time. So we discussed TBN in your engine oil, but on your hydraulic or gear oil you will not see TBN. You will see TAN, or total acid number. Because gear and hydraulic fluids do not have to combat acid-producing contaminants like an engine does, we care less about the amount of base additives in reserves to combat acidic contaminants. However, gear and hydraulic oils are still subject to oxidation, which will increase the acid. So we focus on the total acid number, not the total base number. TAN and TBN have an inverse relationship. As one increases, the other decreases. A high TBN is good, a high TAN is bad. So comparing the TAN of a used oil to the TAN of a new oil will indicate how much the oil has oxidized. And just like TBN, we can use TAN to help determine the life expectancy of the oil.